Hello and welcome to today's lecture on medium access control. This is the first lecture on medium access control. We shall cover this topic with 2 or 3 lectures, as you will see. So far we have discussed about the various switched communication network, where communications were mainly done by using multiplexing, by using switching through the transmission media. But here you will see that the communication will be done using a broadcast media, and which will require some medium access control technique. Let us have a look at the outline of today's lecture. First, I shall introduce to you the need for medium access control technique and explain to you the various broadcast networks in which medium access control technique is relevant. Then we shall discuss various issues in medium access control techniques and consider various goals of medium access controls. Then I shall give an overview of various medium access control techniques. However, in this lecture we shall discuss only random access medium access control techniques such as Aloha, CSMA/CD and CA. This one we shall cover as in the next lecture. And on completion, the student will be able to explain the goals and requirements of medium access control techniques. They will be able to identify key issues related to medium access control techniques, and they will be able to give an outline of possible MAC techniques. Then they will be able to distinguish between centralized and distributed medium access control techniques and classify various contention based techniques such as Aloha, CSMA, CSMA/CD and CSMA/CA. And finally, they will be able to compare performance of contention based techniques. As I mentioned, the networks can be broadly divided into 2 types. One is switched communication network, where peer to peer communication is performed with the help of transmission lines, multiplexers and switches. We have already discussed about switched communication network, and where you have seen how the multiplexing and switching techniques are used in networks such as telephone network, then SONET network, where circuit switching techniques are used. Then we have also discussed various packet switch networks such as X.25, then your frame relay and ATM. These are essentially switched communication network, either packet switching or circuit switching is used, and where techniques like multiplexing and switching are used. Now, let us consider a different kind of scenario in which we have a medium which is shared by a number of users. Say this is the shared media, and here this is user 1, this is user 2, this is user 3, this is user 4 and so on. A particular user will broadcast the data into the network. So, any user will broadcast the data into the network. Now, whenever it is broadcasted, obviously there is a possibility that several users will try to broadcast simultaneously. That is one problem. Second problem is whenever a particular network is broadcasting, particular user is broadcasting, it has to go to proper destination, and so this is some kind of shared medium where essentially broadcasting is being done. Let us have a look at some of the examples. One important example is multi-tapped bus. Say you have got a bus realized maybe by using coaxial cable, and you can have taps to which different users can be connected. You can make several taps, and then n users can be connected, user 1, user 2, user n. So, in this way n users can be connected to a common medium, that is coaxial cable. Now, if A launches some data on the medium, it will proceed in both direction and it will reach 1 and n, 1 and all the others sources, all the other stations connected to the medium. That means, here a particular user is broadcasting and it is going to it is being received by all other users which are connected to the medium. So, this is the multi-tapped bus, and you will see that this type of multi-tap bus is used in local area networks, LAN environment. Let us consider another example, that is ring networks sharing a medium. So, you have got a number of users, say user 1, 2, 3, 4. By users we mean you have, these are essentially the computers, then they are connected with the help of point to point link, and you see they form a ring. So, this particular user 2 is connected to its neighbors 1 and 3, 3 is connected to 2 and 4, 1 is connected to 2 and 4. So, in this way they are connected, and this particular medium may be realized by using twisted pair, or it may be realized by using say optical fiber. It is possible in this type of point to point communication, optical fiber. In both cases you will see that this medium is being shared by all the users. For example, whenever user 1 or station 1 wants to send to 3, it has to go through this part of the medium. Whenever it sends to 4, it will go in this manner. So, this part of the medium is being shared by all the users for data communication. So, this is ring networks using a shared medium. This is another example of broadcast networks. Third example is satellite communication. Here we see that sharing is being done by using uplink and downlink frequency bands. For example, as you can see, each ground station is communicating with the help of a transponder, and there are two frequencies, one is uplink frequency, another is downlink frequency. You can see the uplink frequency is being shared by all the users for communication with the satellite. On the other hand, the downlink frequency is broadcast, it is going to all the ground stations. So, if this particular station, ground stations wants to broadcast, it will send it using uplink frequency, then the satellite will receive it and retransmit or broadcast to all the other ground stations. So, this is the example of satellite communication, where the uplink frequency is being shared by a number of ground stations. Of course, the downlink frequency is broadcasted, so it is being received by everybody, but the uplink frequency is shared by all by using some mechanism. So, this is another example of broadcast networks. Then, apart from satellite, multi-tap bus and ring networks, there is packet radio networks, as you shall see, where also used broadcast networks and wireless communication stations sharing a frequency band. We shall see that wireless communication such as cellular network or packet radio network, in all the cases some bands and some frequency bands are shared. So, these are all examples of broadcast networks. Now, question arises, how different users will send through the shared media. So, it is necessary to have a protocol or technique to orchestrate the transmission from the users. That means, at a time only one user can send through the media, and that has to be decided with the help of this medium access control technique. So, the communication has to be orchestrated by using some protocol or technique, and that is essentially medium access control technique. So, question arises, who goes next? This is the question to be answered. We have seen there are a number of users or stations who are vying for communication, who are trying to get hold of the medium for transmission. Who will go next? That will be decided by the medium access control techniques. So, the protocol used for this purpose are known as medium access control techniques. And this basic purpose, you see the key issues in medium access control techniques are where and how. These are the two basic questions which are to be answered whenever we consider medium access control techniques. Let us see what do these two means. By where we mean who does the control, whether it is performed in a centralized manner or it is done in a distributed manner. Let us see the case of centralized one. In centralized one, a designated station has an authority to grant access to the network. That means a designated station will grant access to the network to the remaining stations. So, it is somewhat like there is a meeting going on and there is a chairman, and chairman can permit any other person who is in the meeting to speak. So, it is somewhat like that. And this centralized scheme has a number of advantages, because there is that the stations will have very simple logic, because the medium access control is being performed by a centralized node, centralized station. The other stations will have very simple logic. So, when they will be permitted, they will simply transmit the data. So, there will be no medium access control logic necessary in each station, only the central station will have the logic. So, the hardware or the software, whatever is used, that will be minimum in case of this scheme in all other station except the central controller. And it has another advantage, it is capable of greater control to provide features like priority, overrides and guaranteed bandwidth. By priority we mean, you see, there may be a number of users and some of them have some important data to send. So, the central controller can give priority to a group of users compared to others. Another is, so whenever a high priority user tries to send data, a low priority data transmission can be stopped. So, it can be overridden with the help of the centralized controller, and it can also guarantee the bandwidth that can be allowed to each user. So, these are the control which can be very easily performed with the help of this centralized controller, and it can do very easy coordination. However, it suffers from lower reliability, because if the central controller fails, then there will be nobody to control. So, the reliability is very poor here if it is dependent on the failure of the central controller. So, if the central controller fails, the medium access control cannot be performed by other users. So, this is the limitation of the centralized controller, and that is why distributed control is preferred in many situations. And in distributed control, stations are can dynamically determine the transmission order. That means, here each and every station take part in the medium access control operation. So, it is done in a mutually agreed upon rule or protocol. So, that is why the distributed control performs it in a dynamic manner, where each and every station takes part. Obviously, it is much more complex, however, it is much more reliable. So, it can tolerate some failure. If some of the stations fail, it does not matter, it will continue, and it is also scalable. By scalable we mean it is easier to have, say, whenever a station joins the network or takes out, it is a particular station is switched off. So, all these things can be taken care of in a distributed medium access control technique in easy manner, and it is very scalable. You can keep on increasing the number of stations very easily in a distributed environment. So, these are the two questions to be answered, and second question is how, where and how. Now, how means it can be performed in a synchronous manner or it can be performed in a asynchronous manner. We have already discussed about that synchronous time division multiplexing, TDM, where we have seen that specific capacity is dedicated. We have seen that each slot is allocated to a particular user or station. As a result, the bandwidth is dedicated, and bandwidth or capacity is dedicated in synchronous time division multiplexing. It can be also done by using frequency division multiplexing. So, here these are all synchronous techniques. On the other hand, in a synchronous technique, the capacity is allocated dynamically. This asynchronous technique is very important for data communication. The reason for that is we know that the data is bursty in nature. So, whenever the data is bursty in nature, there is no point in providing dedicated capacity, because if dedicated capacity is allocated, it will not be utilized. That is why in bursty environment it is necessary to use asynchronous technique such as asynchronous time division multiplexing, ATDM, and where the capacity can be allocated dynamically. So, how means as in asynchronous manner. That is why we will see most of the medium access control techniques that we shall discuss will be based on asynchronous techniques. Now, the medium access control technique designer has a number of goals to satisfy. So, these are the various goals or objectives. First one is initialization. What do you mean by initialization? Whenever you put the network on in the beginning, then it should go to a stable state. That means who will be transmitting first, who will be transmitting next, and so on. There should not be any chaos. So, that as the network is first turned on, it should go to a stable state. That is your initialization. Initial condition will be satisfied. Second is fairness. We have seen that you have got a number of stations who are trying to send data through a shared medium. Obviously, each and every node has to be given equal opportunity. By that we mean the time provided to each station, the time for access has to be fixed, and the delay, that means after some amount of time each and station has to wait for some time, that delay should be also same for each and every station. So, this is your fairness which has to be guaranteed by the medium access control techniques. Then the another important goal is limitation to one station. We have seen that there are a number of stations trying to send. So, at the end medium access control technique should ensure that only one station transmits, and also it is being received by one station, and the only one packet or one packet of data, not multiple packet, will be received by the station, and if multiple packets are there, it should be sent in a orderly manner. So, receipt of packets has to be performed in a orderly manner. It will also perform error limitation, it will do error detection and correct it. Then recovery. So, whenever there is some failure, the medium access control should be designed in such a way that it is able to recover from the failure. And then comes the question of reconfigurability. As I mentioned, stations will be added, removed from the network. So, the medium access control should be able to reconfigure the network so that it can perform the medium access control in an effective manner. Then comes the question of compatibility. Compatibility is important because there will be some standard medium access control technique. If different manufacturers build equipment, they should be able to operate with each other. So, that is your compatibility that has to be ensured. Finally, comes the question of reliability. The medium access control technique should be able to work under the condition of failure and other problems. So, reliability has to be ensured by the medium access control techniques. Now, let us consider the various MAC techniques that is being used. As you can see, it can be broadly divided into 4 types: random, round robin, reservation and channelization. So, these 4 categories are needed in different situations, and in this lecture we shall focus on the random techniques. So, we shall discuss about the other techniques in subsequent lectures. Let us focus on the random techniques, which is very suitable for bursty nature of traffic. So, this random medium access control techniques again can be divided into 4 different types: Aloha, CSMA, CSMA-CD and CSMA-CA. We shall discuss each of them one by one. Let us first consider the first one, that is your Aloha. This Aloha was developed for packet radio network by the University of Hawaii. As you know, Hawaii, that this particular location comprises of a number of islands, and these islands are, obviously you cannot set up a wired network. So, in the University of Hawaii, there was a central computer, and there were terminals distributed in different islands. So, it is necessary for the central computer to communicate with the terminals, and for that purpose Abramson developed a protocol which is known as Aloha for this kind of an environment, and this is the basic environment is mentioned here. The central node, which is essentially the central computer located in the University of Hawaii, and these are the various terminals. This is the terminal 1, this is terminal 2 and this is terminal N located in different islands. So, they communicate by using wireless technique which is known as packet radio. Now, the basic technique is shown here. You see, each of these stations can transmit by using a uplink frequency F1. So, which is random access, which is shared by all the terminals. On the other hand, the central node, after receiving whatever it is being received from all other stations, is retransmitted by using a frequency F2, downlink frequency F2 by the central controller, central station, central computer, and this is being received by all other stations. So, this is the basic environment for which the this Aloha protocol was designed. It works like this: any station who has some data to send will send it. So, it can be considered as a free for all. So, anybody who has data to send will send it. Now, in such a case, obviously there may be some collision. As you can see here, there is a packet of duration TF. This is the frame transmission time. This is the packet duration. As you can see, the vulnerable period is 2 into TF. So, if a packet is transmitted within anywhere within this range, will overlap with this. So, this packet will overlap with any packet transmitted within the range 2 TF. So, as a result, what will happen, collision will occur, and this central node will send the garbled packet, and whenever the garbled packet is received by all other stations, they know that packet has not been transmitted successfully. So, the terminals will perform retransmission. So, retransmission technique is used here for whenever there is a collision. Now, let us see how it is being done. So, as I mentioned, this is the vulnerable period, which is equal to 2 TF, and a collision can occur within this period whenever there is multiple stations, multiple terminals sends data. Then there is a maximum propagation time. We have seen that there will be some round the that from the terminal it will go to the central node, and from the central node again it will come here. So, this round trip delay is essentially this 2 into t propagation time. So, this is the timeout period. That means after the vulnerable period, you can see here T0 plus Tf and 2 Tf. So, this was the after a successful transmission, this is the vulnerable period, and within this time that T0 plus Tf plus 2 Tf, all other stations will come to know that a collision has occurred. Now, if multiple stations take part in sending and collision occurs, and if they immediately send, there will be another collision. So, that is why the stations wait for some random amount of time. This is known as backup. So, the stations wait for random amount of time, then again they do the retransmission. So, this is your retransmission. So, the retransmission is being performed by all the stations, but the backup time is different for different stations. So, you see after a packet is transmitted, it has to wait for this much duration for another packet when it is retransmitted, and this backup time is random in nature, so that the collision does not occur second time in this. Let us see how the performance can be improved in this case. Now, we have seen that in the previous case, which is known as pure aloha, the vulnerable period is 2 into t, that is your transmission time. Now, Roberts proposed a technique which is known as slotted aloha, and in this technique the time is divided in slots, equal slots. Then the packet transmission can be started only in the beginning of the time slots, here, here, here or here, not in between. So, in case of pure aloha, transmission can start any time. So, as a consequence, if there is no collisions, there will be no collision, and whenever there is overlap, say this is your sender A, this is your sender B, this is sender C. So, if there is overlap, there will be overlap for the entire frame, not part of the frame as it happened in case of pure aloha, and as a consequence in this case the vulnerable period is reduced from 2 TF to TF, and this will lead to better performance of this slotted aloha technique. Let us see how the performance varies. Now, as you can see, this G, which is the offered load, that the number of attempts made per packet time, and if the number of attempts made per packet time increases, as you can see, if it reaches 0.5 in case of pure aloha, then you get maximum throughput, and maximum throughput is S is equal to G into e to the power minus 2G. That means for G is equal to, and it happens when G is equal to 0.5, 0.5. So, in this case the value of S will be equal to 0.5 into e to the power minus 2G, G is 0.5. So, it will be equal to 1 by E. So, value is essentially 0.184, roughly 0.184. That means, we can see that maximum throughput, that is your S, that you can achieve is only 18%, roughly, which is equal to 18%, and which happens whenever the offered load is 0.5. That means, number of attempts per packet is 0.5, and as the more packets are introduced, the throughput decreases, and it may become 0 whenever there are the offered load is very high. That means, as the load increases, there is a possibility that the throughput will become 0. So, this Aloha works only when the traffic is very small and the network is very lightly loaded. So, less than 18%. However, by using slotted Aloha, we can see that performance improves, and it can and as you can see here, the maximum throughput is received whenever G is equal to 1. So, whenever G is equal to 1, the maximum throughput that you can get here is, in this particular case, in the previous case it was 1 by 2 E. So, in this case it will be equal to G, it is S is equal to, this is for slotted the pure Aloha, but in this case S will be equal to 1 by E. 1 by E will be equal to 0.36368. So, we find that the performance maximum throughput that you can achieve in this case is about 37%, 36.8%, 37%, which is double that of pure Aloha. So, by using slotted Aloha, the performance is doubled in case of slotted Aloha compared to pure Aloha. Now, let us look at the limitation of this technique. We have seen that when a station sends a packet, others know about it within a fraction of packet transmission time. So, usually the packet transmission time is much longer than the propagation time. I mean, packet transmission time is much longer than the propagation time, because these are very closely located. So, but in case of pure Aloha, slotted Aloha, what was done, the medium was not checked before sending the packet. So, if already a packet transmission is going on, a station starts sending packet, that is being overcome in CSMA. So, based on this observation that the other stations come to know about it within a fraction of the packet transmission time, why not monitor the medium? So, this led to the development of carrier sense multiple access protocol, which is essentially based on station listens the medium before transmitting, or it is based on listen before talking. That means, first you check the medium, if it is free only then you send it. So, the collision will reduce, and it has got two varieties, non-persistent and persistent. So, let us see in non-persistent what happens. So, each station senses carrier is sensed. If it is busy, then it waits for random amount of time, that is in case of non-persistent. On the other hand, in case of if it is not busy, then the packet is sent. On the other hand, in case of persistent protocol, if the medium is busy, it again senses it. It does not wait for random amount of time, it keeps on sensing, and then whenever it is not busy, it sends packet with probability, with some probability. So, that these are the two basic variations. Let us see how exactly it happens. So, we have seen that in case of non-persistent, if the medium is idle, the packet is transmitted. On the other hand, if the medium is busy, wait random period, then resense the medium once again. So, after resensing, if it is busy, again waits for random amount of time, and if it is not busy, it is transmitted. In case of that persistent, there are two varieties. It is in case of one persistent, if the medium is idle, it transmits, and if the medium is busy, continue to listen the channel continue to listen until the channel is sense idle, then transmit immediately. So, it does not wait for with probability. So, rather it transmits with probability 1. On the other hand, in P persistent, if the medium is idle, transmit with a probability P. So, it may transmit, it may not transmit. That is the advantage of P persistent. So, these are the three basic techniques used here, and in this particular case, let us see what is the vulnerable period, because vulnerable period plays a very important role so far as the throughput is concerned. So, in case of CSMA, as you can see, the packet is going from one end to the other end of the network, and that and by the time it reaches the other end, and if no collision take place, then within one propagation time, the station captures the medium. So, in other words, we can tell that the vulnerable period is T propagation time, and we know that the propagation time is usually small compared to the transmission time. That is why the vulnerable period is relatively smaller in case of CSMA technique. However, the throughput depends on a parameter known as A, where A is equal to propagation time by transmission time of a packet. So, this ratio propagation time by transmission time plays a very important role, and that decides the throughput. As you can see, we have not given any analytical expression for throughput, but here it shows how the throughput varies as the value of A changes. As you can see, whenever A is equal to 0.5, that means propagation time by transmission time is 0.5. That means propagation time is relatively high compared to transmission time, about half of the transmission time. Then A is equal to 0.5, then this is the throughput. It is about 0.36, very close to the slotted aloha. On the other hand, as the value of A becomes smaller and smaller, the throughput increases, and that is why the that parameter plays very important role, and it is necessary to have smaller propagation time and relatively larger transmission time to have higher throughput in CSMA protocol. Now, we find that this CSMA protocol has a very serious limitation. The limitations comes from the fact that, suppose here a particular station starts transmission of packet. Now, and this is the propagation time, maximum propagation time through a particular medium. Say this is the network, this is one station A, and here at the other end you have got another station B. Now, B comes to know about it within this time, but the packet transmission time can be quite long. So, although a particular station transmits it and then the other end receives that packet, it can easily find out whether the medium is busy or not. But what happens, this particular station, even after detecting that collision has occurred, it may, if it has started transmission, suppose somewhere here, it will continue transmission. So, this part of the time, both the packets will overlap, not only this part, but this part of the time. So, by this time, this station has come to know about that collision has occurred. In spite of that, it has not stopped transmission, and neither the previous station stops transmission. As a result, what happens? The time is wasted. This wastage of time is minimized in CSMA CD, carrier sense multiple access with collision detection. So, in carrier sense multiple access with collision detection, the station listens to the medium while transmitting. That not only it listens to the medium before transmission as you do in carrier sense multiple access, but it does some additional thing. It listens while transmitting. That is why it is called listen while talking, LWT. And here also there are three cases, that non-persistent, one persistent and P persistent. As you know, if the channel is idle, the packet is transmitted if non-persistent or one persistent. Now, for P persistent, the packet is sent with probability P or delayed by the end-to-end propagation delay with probability 1 minus P. That means, If the channel is idle, it is immediately transmitted for non-persistent and one-persistent. For p-persistent, the packet is sent with probability p or delayed by the end-to-end propagation delay with probability 1 minus p. So, as we know, for p-persistent, even when the channel is idle, it may be sent, may not be sent. On the other hand, if the channel is busy, the packet is backed off and the algorithm is repeated for non-persistent case. And the station defers transmission until the channel is sensed idle, then immediately transmit in case of one persistent case. For p persistent CSMA CD, the station defers until the channel is idle, then follow the channel idle procedure. So, we see this channel idle procedure we have to understand the CSMA CD protocol, but the basic idea is this, that whenever the channel is found to be idle, packet transmission is started and the stations keep on monitoring the medium, and whenever a collision is detected, some jamming signal is introduced to inform all the stations so that that collision has occurred. Then all the stations backs off and they wait random amount of time before transmitting another packet. That is the basic idea. Let us see how it really happens. But before that, let us see what is the minimum requirement for collision detection in CSMA. Here we see, suppose station A starts transmission at time t is equal to 0 and the packet moves towards the direction of B, which is at the other end, and before this packet reaches B, it starts transmission again another packet which goes towards another direction, and at time whenever this packet reaches, it detects collision, and whenever this packet reaches the other end, it detects collision. So, we find that for detection of collision by both ends, the period that is required is 2 t propagation, and twice the propagation time is required for detection of collision, and that means the packet should be, that transmission of the packet should be longer than the 2 propagation time. That is the requirement for detection of collision. That means collision is detected how? A packet is transmitting, a particular station is transmitting a packet, and if it receives some other signal, some other carrier, then it detects collision. To do that, the requirement is that the packet time, transmission time, that means t transmission time should be greater than equal to 2 into t propagation time. This condition, if it is satisfied, all the stations will be able to detect collision. If it is smaller than that, in this situation what can happen, the packets may collide in the middle. That means, if this packet is small, it may go in this direction, and whenever before it reaches this, the transmission is finished, and whenever the transmission starts here from here, it will send another packet, and again both the packets will cross each other in the middle, and collision will only be detected by the middle station, but not by all other station, not by the senders. So, to ensure that, this is the requirement. Now, I mentioned about the backup time, and this is known as, this is the binary backup algorithm that is being used in CSMA CD protocol. Here we see that whenever packet is ready, it checks whether it is deferring or not deferring, whether it is waiting for some time or not. If it is not waiting, then it starts transmission, and as I mentioned, while transmitting, it keeps on monitoring to detect collision. If collision is not detected, then the transmission is finished, and however, then the transmission is done, transmission is successful. On the other hand, if the collision is, the transmission is not finished and collision is detected, then it sends a jamming signal, and after sending the jamming signal, it has to decide about how long it will back off, and for that purpose it has to find out how many attempts it has already done. So, it will increment the attempt from the previous one, and it will check whether the number of attempt has exceeded 15, some number, maximum number that is allowed. If the maximum number is allowed, it computes backup and waits for that backup time. So, let us see how the backup time is calculated. For that purpose, a number r is found out, and how it is found out? It finds out a value between n and 10. N is the unsuccessful attempts. Say whenever it is the first attempt, then value of n is equal to 1. So, in such a case, it will wait between say 0 and 2 to the power 1 is 2. That means 2 to the power 0 is first attempt is unsuccessful attempt is 1. So, it will be 0, 1 and 2. So, these are the three possible cases, and this is being multiplied with some time slot, and that time slot is multiplied say delta t. So, that delta t is multiplied with this, and that is the backup time. Now, after 2 backup, say whenever the n is 2, then what will happen? This k will be equal to 2 and value will be 0, 1, 2, 3 and 4. So, it will choose between 1 to 4, 0 to 4, and then it may send immediately, or it will send for up to 4 delta t amount of time. So, in this way it will keep on increasing, and maximum time can be 2 to the power k 2 to the power 10, that means 1024 delta t, which is quite high. That means the backup time randomly increases as the number of attempts increases. And what can happen whenever the number of attempts exceeds 15, then the packet is discarded, because excessive collision is occurring. Packet is, that means the network is heavily loaded. So, in such a situation the retransmission is not performed. So, we find that in case of CSMA CD protocol, whenever the number of collisions exceeds 15, a packet may not be transmitted. So, we cannot guarantee that packet will be always delivered to the destination. However, whenever the traffic is less, that means load is less, the number of collisions will be less, then the packet will be delivered. In other words, that CSMA CD protocol works fine whenever the load is less. And this the CSMA CD protocol, as you can see, has got 3 distinct states. First one is contention period. After a successful transmission, there will be some contention period. Contention period is essentially during which all the stations will try to contend to get hold of the medium, and we have already seen that binary backoff algorithm which is being used to resolve the contention, and after the contention is resolved, a particular stations get hold of the medium, it performs the transmission. And however, if the network is very lightly loaded, there may be some idle period, and after the idle period again there can be some contention period, then packet transmission, then contention period, then packet transmission, or idle period. So, we find that in the CSMA CD protocol it will be in one of the 3 states, either it will be transmitting a packet or through the medium, or there will be some kind of contention algorithm going on, contention mechanism going on by using binary backoff algorithm, and then all the stations will try to get hold of the medium, and ultimately one of the station will be able to get hold of the medium and send the packet. So, this is how the CSMA CD works. Now, let us look at the performance of various protocols. Let us compare the performance of different protocols that we have discussed so far. So, here we see the that pure Aloha we have already seen. that in case of pure Aloha, the maximum throughput that you can achieve is only about 18%, and that happens whenever the value of G is equal to 0.5. In case of slotted Aloha, the performance improves to about 37%, and which occurs when G is equal to 1. And for one persistent CSMA, we find that the throughput is roughly very close to 60%, and for non-persistent CSMA, as you can see, the throughput is increasing. Here actually these two values, this is non-persistent CSMA and this is the non-persistent CSMA CD. We find that for non-persistent CSMA CD we get the maximum throughput, which is very close to 1. However, whenever the load increases high, it becomes very high, then of course it becomes unstable and throughput reduces, and it may reaches the thrashing situation in case of both non-persistent CSMA and non-persistent CSMA CD. And here all these curves have been plotted for a particular value of A, which is maybe roughly equal to 0.01, which is, that means the packet transmission time is roughly 100 times that of propagation time. So, propagation time is assumed to be very small compared to the transmission time. However, if the propagation time is not very small, then there is a possibility that the transmission, then the throughput will not be very high. So, we find we have in this lecture we have discussed about various techniques based on contention, or which are based on random techniques. There is another protocol which is known as CSMA CA, which is also based on contention, which is used in wireless LAN, wireless applications, which I shall discuss in the next lecture. But let me summarize the techniques that we have discussed in this lecture. Here we have seen that Aloha, which is the simplest one, works fine whenever the traffic load is very small, and it is the simplest technique, simplest contention based technique. Then the slotted Aloha, which is an improvement over CSMA CA. There the performance is better, little better, double that of the pure Aloha. However, in this case the packets are to be synchronized, and as a result some synchronization mechanism has to be devised. The central controller may keep on sending some signal to all the stations, and they will send in the synchronized manner. On the other hand, in case of CSMA, that means by monitoring the medium, carriers sense multiple access, that means which is essentially listen before talk. By monitoring the medium, the performance can be significantly improved, in this case as you can see, over slotted Aloha or pure Aloha. And as you can see, the non-persistent CSMA performs better than one persistent CSMA. The reason for that is, in one persistent CSMA it is prone to more collisions, because it is a more greedy approach compared to non-persistent CSMA. And by using that collision detection scheme, that carriers sense multiple access with collision detections, throughput can be significantly improved, and as you can see it may reach very close to 1. However, whenever the load is very high, then they will not be stable and the throughput will decrease and it may reach thrashing situation. Now it is time to give you review questions based on this lecture. Question 1 is, in what environment it is necessary to have medium access control for data communication? Second question is, how performance is improved in slotted Aloha compared to pure Aloha? Third question is, distinguish between persistent and non-persistent CSMA scheme. Fourth question is, how does the efficiency of CSMA based schemes depend on A, which that parameter, propagation time by transmission time, that ratio. And fifth question is, how performance is improved in CSMA CD over CSMA technique. So, these are the 5 questions. based on on today's lectures, and these questions will be answered in the next lecture. Here are the answers to the questions of lecture number 24. The first question was, what are the benefits of cell switching used in ATM? In the last lecture, we have discussed the ATM network, and we have seen that in ATM network cell switching is being performed. The answer is, the key features of ATM are connection oriented service using virtual circuit, and data transfer is using 53 byte fixed cells. So, it does cell switching. So, by using cell switching, we have seen that cells reach different destination in the form of a continuous stream. That means the delay is small because of high speed and small size of the cells. So, the cell switching has the benefit of smaller delay in ATM network, and also switching and multiplexing by hardware at the cell level. So, makes the implementation inexpensive and fast. So, ATM networks, as we know, is very fast. Minimum speed is 154.5 megabits per second, and the other speeds are still higher. And actually, the physical layer that is being used is SONET, synchronous optical network, and there this is the minimum speed that is being used. Second question was, what are the relationship between TPs, VPs and VCs? The connection between two endpoints is accomplished with the help of the TP, the transmission paths, virtual paths and virtual circuits organized in a hierarchical manner. As we know, the transmission path is the physical transmission media. Usually it is, in case of ATM, it is optical fiber used to link 2 points, and in each transmission path virtual circuits are logically divided in separate virtual paths, and each virtual path in turn carries several virtual circuits. So, it is a hierarchy. So, each transmission path will have several virtual path. This is your VP, this is your TP, and each virtual path will have several virtual circuits. This is your VC. This is the relationship between VP, TP, VP and VCs. Third question was, what is an ATM virtual connection? How is an ATM virtual connection identified? Answer is, a virtual connection is identified by pair of numbers VPI and VCR, that is your virtual path identifiers and virtual circuit identifiers. We know that this is a 12-bit number and this is a 16-bit number. With the help of this, it is identified. Fourth question was, how cell boundaries are identified in ATM? The answer is, nodes make use of fixed cell size and HAC, that is your header error control, to determine the cell boundaries implicitly, as we have discussed in the last lecture. Last question was, how congestion control is performed in ATM? Answer is, exercising admission control, selecting the route of admitted connections, allocating bandwidth and buffer to each connection, selectively dropping low priority cells, asking sources to limit the cell stream ratio. So, these were the 5 questions given in lecture number 24, and with this we come to the end of today's lecture. In the next lecture, we shall discuss about that CSMA CA protocol, and also we shall discuss about the control access techniques. Thank you.